Hello all, welcome to the video lecture. This is Ramesh Lama. In this video, we'll be discussing about the Hadoop distributed file system. As we have been discussing about the big data analytics tools and the tools and systems, in our last class we discussed about the different big data analytics tools that are in use nowadays, and one of the most commonly used tool is the Hadoop, and we also discussed about the ecosystem of the Hadoop and the different components that the Hadoop ecosystem consists. And in this video we'll be discussing about the one of the component that is in use, uh, that is being used by the Hadoop ecosystem, or uh, that is the one of the component of the Hadoop ecosystem, and it is Hadoop distributed file system, or HDFS. And the HDFS is one of the core components of the Hadoop framework, and it is mainly responsible for the storage or file storage. And the HDFS is the distributed file system, and a part of the large file can be stored on the different nodes across the cluster, and it is distributed, reliable, and scalable file system. And using the HDFS, the main data is stored in the multiple data nodes, and it is also replicated. And when data node is down, the data can be accessed through uh, any other data node which is uh, available and which contains the replication. And it is very cost effective as it uses the very simple commodity hardware to process and store the data blocks. And let us see in detail about the HDFS architecture. And this HDFS architecture is a block structured file system, and where each file is divided into the blocks of the predetermined size, and these blocks are stored across the cluster of one or several machines. And this architecture follows the master and slave architecture, where a cluster, um, where the cluster comprises of a single um, name node or the master node, and all other nodes are the data nodes or the uh, slave nodes. And this SDFS can be deployed on the broad spectrum of the machines that support Java, though one can run the several data nodes on the single machine. But in practical world, the data nodes are spread across the various machines. So now we'll see in more detail about this the component, that is the master node or the name node and the data nodes. Well, talking about the name node, it is the master server, and it manages the file system namespace and regulates the access to file by the clients. uh, and the master node in the HDFS architecture maintains and manages the blocks present on the data nodes or the slave nodes, and mainly it stores the metadata of all the file, including the information about the data nodes, and file stored like the files stored on the HDFS and the replications. Actually, it doesn't store the data by itself. It stores the metadata which contains the information regarding the data nodes and its replications, and file stores on the HDFS. And let's see the function of name node. As we have said before, it consists of the metadata, and it's the daemon that maintains and manages the data nodes or the uh, slave nodes, and it records the metadata of all the files stored in the clusters. For example, the location of blocks stored, the size of files, the permissions, hierarchy, and so on. And there are two files associated with the metadata. One is the FS image, which contains the complete state of the file system namespace which since the start of the name node, and another one is the edit logs. It contains all the recent modification made to the file system with respect to the most recent FS image. It basically records each changes that takes place to the file system metadata. For example, if a file is deleted in the Hdfs, the name node will immediately record this in the edit log. Uh, so this is all about the name node, and another component is of the architecture is the data node, and the data nodes are slave nodes in the SDFS. Unlike the name node, data node is commodity hardware, which is like the non-expensive system, and which is not of a highly which is not of the high quality or the high availability. And the data node is a block server that stores the data in the local file format, that ext3 or ext4. And now talking about the function of the data nodes, these are the slave nodes or slave daemons are the process which runs on each machine, and mm, the actual data is stored in the data nodes, and the data nodes perform the low level read and write requests from the file system's client, and they send heartbeats to the name node periodically to report the overall health of the SDFS. And by default the frequency is set to the 3 seconds. That means it keeps on updating the status of the SDFS, or the status of the or the health of the overall health of the SDFS to the name node. And apart from these two daemons, uh, there is a third daemon or the process which is known as the secondary name node. This secondary name node works concurrently with the primary name node as a helper daemon, and the secondary name node is one which constantly reads all the file systems and metadata from the RAM of the name node, and it writes it into the hard disk or the file system, and it's responsible for combining the edit logs with the with the FS image from the name node. And another important component of the SDFS is the data blocks. It is like it can be considered as a standard unit of data or files which is stored on the SDFS, and these data blocks are minimum size of the data that can be read or write in one shot. And in general, in any file system, we store the data as a collection of blocks, and this stores each file as blocks which are scattered throughout the Apache Hadoop cluster, and the default size of the block is 128 megabyte in Apache Hadoop, and which can be configured as the requirement as per the requirement. Like this size 128 MB means it is the like two multiple of the 64 MB in Apache Hadoop, and uh, it can be configured as per our requirement. And suppose if we are about to store, or if we are about to uh, like suppose we are about to process the file, or we are about to save the file. For example, the example, the txt file, and the size of it has a size of 514 megabyte, as shown in figure. Suppose that we are using the default configuration of block size, which is 128 MB. Then we will be creating 5 blocks, and the first 4 blocks will be 128 MB, but the last block will be of 2 2 megabyte size only. So in this way, we will divide the block into the small sub blocks. Like we will divide the data into the different blocks of size. Like if we have a 128 MB as a default size, then it will be made of the different blocks of the size of 128 MB. And uh, and then next we will process, or we will store these data blocks. And as we have discussed before, like we get the fault tolerance, or we the data is stored in the replicated manner. So let's see how the replication is achieved, or how replication is done in the Hdfs. As the Hdfs, as we discussed about the block, let us see how the replication of these blocks take place in the Hdfs architecture. This SDFS provides a reliable way to restore the huge data in the distributed environment as the data blocks. These blocks are also replicated to provide fault tolerance, and the default replication factor is 3, which is again configurable. And as we can see in the figure here, that each block is replicated 3 times uh, and stored on the different data nodes. Like here we consider the default replication factor, like the suppose we have the size of 128 MB, and if we are storing the file of size 128 MB in the Hdfs using the default configuration, we will end up occupying the space of 384 megabyte, which is 3 times of the 128 megabyte, as the blocks will be replicated 3 times, and each replica will be residing on the different data node. And the most important thing that we have to be noted here is the name node collects the block reports from the data node periodically to maintain the replication factor. Therefore, whenever a block is over replicated or under replicated, the name node deletes or adds the replicas as needed. As we can see here, we get the replication, like the node 1 consists of this block 1 is stored in the node 1 as well as in the node 2, similarly in the node 4. And block 4, we can see block 4 is stored in the node 1, node 2 and node 3, and block 2 is stored in block node 2, node 3 and node 4. In this way, the replication is done, or in this way the replication management is performed. And the another term is that is used in case in Hdfs is the rack awareness. The rack awareness is like, let's see what is the rack awareness. Basically, let's see what is rack, and then we'll see the rack awareness later. The rack is a physical collection of nodes. We can see here different racks: rack 1, rack 2 and rack 3, and it consists of the different nodes. And it is the collection of nodes in our Hadoop cluster. The large cluster consists of many racks, And with the help of rack information, name node chooses the closest data node to achieve the maximum performance while performing the read and write information, which reduces the network traffic. So this basically the rack awareness is used for the to choose the closest data node. And a rack can have multiple data nodes storing the filed blocks and their replicas. And the Hadoop itself is so smart that it will automatically write a particular file block in two different data nodes in a rack. So if we want to store that block of data into the more than uh, two racks, that we can do that. Also this feature is configurable, means we can change it manually. Again, the name node also ensures that all the replicas are not stored in the same node or the same rack or the single rack. So it follows a kind of built-in rack awareness algorithm to reduce the latency as well as to provide the fault tolerance. So considering the replication factor of 3, the rack awareness algorithm says that the first replica of the block will be stored on the local rack, and the next two replicas will be stored on the different remote rack. We can see here in the figure. uh, and on the different rack, but on the different data node within that remote rack shown in the figure. And if we have more replicas, the rest of the replicas will be placed on the random data nodes, provided not more than two replicas reside in the same rack if possible. So we can see here, like the um, or a rack can have not more than two same blocks in the same rack. And if we have more replicas, the rest of the replicas will be placed on the random data nodes, provided not more than two replicas. And this is how the actual Hadoop clusters look like. And we can have multiple, we can see here, like we have multiple racks populated with the data nodes. And we can see the Hadoop cluster and core switch and the rack switch, and with different racks consisting of the different computers. And one of the advantage of the rack awareness is that it is used to improve the network performance. Like the communication between the nodes residing on the different racks is directed via switch. We can see here the communications is performed through or via the switch. And in general, we will find greater network bandwidth between the same rack than the machines residing in the different racks. So the rack awareness helps us to find to reduce the write traffic in the different racks, and thus provide better write performance. Also, we will be gaining the increased read performance because we are using the bandwidth of the multiple racks. So in this way, the rack awareness helps us to find the nearest like the nearest or the to our nearest nodes. And once we get the nearest node, it will definitely reduce the or it will definitely reduce it will definitely improve the network performance. And let's see let's see how the read and write operations are performed in the Hdfs. This Hdfs follows the write once and read many philosophy, and which means we cannot edit files already stored in the Hdfs, but we can append new data by reopening the file. And first, let's start with the Hdfs write architecture, or how let us see how the write performance write operations are performed in the HDFS. Suppose a situation where an HDFS client wants to write the file named example the txt. We have got the file of size 244 megabyte and its example the txt. And first what we do is the system like the system will we have got the system which is configured with the block size of 128 megabyte by default. So the client will be dividing the file this example the txt into the two blocks. We can see block A and block B, and the one block will be of size 128 megabyte and the block B will have the size of 120 megabyte. Now the following protocol will be followed whenever the data is written into the HDFS. At first, the client will reach out to the name node for the write request against two blocks, say block A and block B. We have got block A and block B, and next the name node will then grant the client the write permission, and it will provide the IP address of the data nodes where the files blocks will be copied eventually. And the IP addresses of the data nodes is purely randomized based on the availability, replication factor, and the rack awareness that have been discussed earlier. And let's say the replication factor is set to 3, like we have set to 3, which is default number. And here what we do is for each block the name node will be providing the client a list of the 3 IP address, like 3 IP addresses of the data nodes, and the list will be unique for each block. And let us suppose the name node provided following list of the IP addresses to the client. We can see here, like for block A, the list A will consist of the IP of node data node 1. Suppose we have got the data node 1, IP of data node 4, and IP of data node 6. Similarly, for block B or the set B, the list will be IP of data node 3, IP of data node 7, and IP of the data node 9. Here what happens is, like, each block will be copied in the 3 different data nodes to maintain the replication factor consistent throughout the cluster. So we got this block. Each block will be stored or will be stored in the 3 different data nodes. And now the whole data call process will happen, and it is done in the here, like as we have seen here, each block will be yeah. So let's see the write architecture in more detail. Here the whole data copy process will happen in basically 3 stages. First is the setup of the pipeline, and next will be the data streaming, and last the replication shutdown of the pipeline will take place, or it is known as the acknowledgement stage. Before writing the blocks, the client confirms whether the data nodes present in each of the list of the IPs are ready to receive the data or not. And in doing so, the client creates a pipeline for each blocks by connecting the individual data nodes in the respective list of the data block. Let us consider, like, first let us suppose we are about to create a pipeline for the block A, and the list of the data nodes provided by the name node is, we have got the list, like for block A we have got the list A, which is IP of node 1, IP of node 4, and IP of the node 6. For block A, the client will be performing the following steps to create the pipeline. We can see here, like, here is the Hdfs client, which is the and it is about to what at the first stage it will, what it does is, like, we can see here in step by step. First, the client will choose the first data node in the list, which is the data nodes of data node IPs for the block A, and which is the data node 1, and it will establish the TCP IP connection, and the client will inform data node 1 to be ready to receive the block, and it will also provide the IPs of the next two data nodes to the data node 1, where the data node is supposed to be replicated. And next, the data node 1 will connect the data node to the data node 4, and the data node 1 will inform the data node 4 to be ready to receive the data block, and it will give IP of the data node 6, and then the data node 4 will tell the data node 6 to be ready for the receiving data. And next, the acknowledgement of the readiness will follow in the reverse sequence, like it will be started from data node 6 to data node 4, and then to the data node 1, and at last the data node 1 will inform the client that all data nodes are ready, and a pipeline will be formed between the client data node 1, data node 4, and 6. And now the pipeline is set up, is complete, the pipeline setup is complete, and the client will finally begin to the data copy or the streaming process. So in this way, the pipeline is set up. And next is the data streaming. So in data streaming, here also the following steps will take place during the replications. Once the block has been returned to the data node 1 by the client, we can see here the data node 1 will connect to the data node 4. We can see here, like, the data node 1 will connect to the data node 4, and then data node 1 will push the block of the pipeline and data will be copied to the data node 4. Again, the data node 4 will connect to the data node 6 and will copy the last replica of the block. We can see here, like, this block A will be be copied from block A to node 1 to node 4, and then from node 4 to node 6. As the pipeline has been created, the client will push data into the pipeline. Now we should not forget that in the Hdfs, data is replicated based on the replication factor. So here the block A will be stored to the 3 data nodes, as assumed the replication factor is 3, and as we move ahead, the client A will copy block A to the data node 1 only, and the replication is always done by the data node sequentially. So the client needs to store, or the client needs to move the data just only to the data node 1. The rest of the replication will be done by the data nodes by themselves. And the last one is the shutting down of the pipeline, or the acknowledgement stage. Once the block has been copied to the 3 data nodes, here a series of acknowledgement will take place to ensure the client and the name node that the data has been written successfully. Then the client will finally close the pipeline to end the TCP session. As we can see here in the figure, the data node 1 will push 3 acknowledgement, like including its own, into the pipeline and send it to the client. And the client will inform the name node that the data has been written successfully, and the name node will update. Here we can see the name node will update its metadata, and the client will shut down the pipeline. And it's the for block B also it will take place in the similar fashion, like the block B is copied into the data nodes in parallel with the block A, and it will also follow the same procedure as in the block A. Like the client will copy block A to the block will copy the block A and block B to the data node to the first data node simultaneously. And here what happens in our case is like the two pipelines will be formed for each of the block, and all the process discussed as like above will be happen in the parallel in these two pipelines. And like the client writes the blocks into the first data node, and the data nodes will be replicating the blocks sequentially. We can see here the shutdown pipeline. Let's see the read architecture as well. So here is an let's take an above example again, where the Hdfs client wants to read the file. Like we have got the example the txt file. Now what it does is like the client will reach out to the name node asking for the block. Here we can see it will go to the name node, and it will ask the client will reach out to the name node asking for the block metadata for the file example.txt, and the name node will return the list of the data nodes where block A and block B are stored. We can see here the IP addresses that is of the DN1 and DN2, and after that client will connect to the data nodes where the blocks are stored. The client starts reading the data parallel from data nodes from block A to block, like we can see the block A and block B. Here the data node 1 and the block A will be read the client will read the data block A from the data node 1, and block B from the data node, we can see here data node 3, and once the client gets all the required blocks, it will combine these blocks to form a file. And while serving read request of the client, the Hdfs selects the replica which is closest to the client. Like it will see the closest client, closest switch or closest rack or and this reduces the read latency and the bandwidth consumption. Therefore that replica is selected which resides the same rack as the reader node if possible. Like we can see here, like the rack 1, it selects the data from the data node from the rack 1 because the block A and block B are resides in the same rack, even though these are available in rack 5 and rack 7 as well. So Let's see when to use the SDFS, or we can see some SDFS use cases. There are many use cases of the SDFS, but SDFS can be used for storing the big data sets for the further processing, and SDFS can be used for storing archive data since it is cheaper, as SDFS allows storing on the low cost commodity hardware while ensuring a high degree of fault tolerance. And basically, in some cases the SDFS may not be preferred. So there are certain scenarios where in which the SDFS may not be a good fit or good choice, uh, like choice. And here are some examples. Like SDFS is not suitable for storing the data related to the application require low latency data access, like as we can see, as compared to other techniques like other tools like Spark. Like the latency is data latency is high. So for some applications, it may not be suitable for applications which requires the low latency data access, which the SDFS may not be suitable in that cases. And it may not be suitable for storing large number of small files as metadata. For each file needs to be stored on the name node and is held in memory. And another is another scenario where the SDFS is not suitable is for the scenarios which requires multiple simultaneous writes of the same file, like as we have discussed before. It is the write only and read many philosophy. It works on the philosophy of write many and write once and read many philosophy. So it may not be useful or it may not be suitable for the scenarios which require multiple or the simultaneous writes to the same file. So it's all about the SDFS. And next we'll be discussing about the MapReduce. Well, MapReduce is we have also discussed about the MapReduce just in brief in our last video. Well, talking about the MapReduce, it is the component, like it is the Hadoop framework. It is the Hadoop framework which is used for writing the applications that can process the vast amount of data on the large clusters, or it can be called as a programming model in which we can process the large data sets across the computer clusters. And this application allows data to be stored in the distributed form, and it simplifies enormous volume of data and large scale computing. And the MapReduce is a component of the it is the component of the Apache Hadoop ecosystem and a framework that enhances the massive data processing. And as we have said before, like it enhances the processing of massive data using the dispersed and the parallel algorithm in the Hadoop ecosystem. And this programming model is applied in some like the for in social platforms like and e-commerce to analyze the huge data collected from the online users. It is just the two example. There are lots of use cases of the MapReduce. And basically there are the MapReduce it consists of primarily two tasks. One is map and another one is the reduce. And we perform the former task before the latter, means we perform the map task before the reduce task. And in the map job we split the data set into the chunks. Our map task processes these chunks in parallel, and the map in the map we use the outputs as the map we use outputs as the inputs for the reduce task. Like we can see the output of the map becomes the input of the reduce. task, and the reducer process the intermediate data from the map into the smaller tuples that reduces the tasks, leading to the final output of the framework. And this map reduce framework enhances the scheduling and monitoring of the task, and the failed tasks are re-executed by the framework. And as we can like this framework can be used easily and even by the programmers with little expertise on the distributed processing. And this MapReduce can be implemented using the various programming languages such as Java, Hive, Peak, Scala, and the Python. And let us see how this MapReduce in Hadoop works, or we can say the architecture of the MapReduce. Basically, the MapReduce architecture consists of the various components, and here we will be discussing. We'll just briefly discuss about the components. And here, the first is, we can see here the job, and this is the actual work that needs to be executed or processed. And there we can see a task, the task, and that we can see the term task here. This is the piece of actual work that needs to be executed or processed. And a MapReduce job comprises many small tasks that need to be executed. Similarly, we can see the job tracker here. This job tracker plays a role of scheduling jobs and tracking all the assigned to the task tracker. And this task tracker plays the role in tracking the tasks and reporting the status of the tasks to the job tracker. And you can see here the input data. This input data is the data used to process in the mapping phase, and the output data, that is the result of the mapping and reducing. And we can see the client or client program. This is the program of application or this is the program or the application programming interface API that submits jobs to the MapReduce, and MapReduce can accept jobs from many clients. And we can see here the Hadoop MapReducer master, and they play the role in dividing the jobs into the job paths. And the job paths are, these are the sub jobs that these are the sub jobs that result from the division of the main job. Basically, in the MapReduce architecture, the client submit jobs to the MapReduce master, and this master will return, then subdivide the master will then subdivide the jobs into the equal subpaths, and the job paths will be used for the two main tasks, which are mapping and reducing. And the developer will write the logic that satisfied the requirements of the organizations or the company. And the input data will be split and mapped. The intermediate data will then be sorted and merged. The reducer will generate the final outputs stored in the Hdfs will process. And the the reducer that will generate a final output is stored in the Hdfs. And let us see, like we can see here, how job tracker and the task tracker work. Like every job consists of two components, mapping task and the reducing task. And the map task plays a role in splitting jobs into the job paths and mapping the intermediate data. The reduce task plays the role of shuffling and reducing intermediate data into the smaller units. And the job tracker acts as a master, and it ensures that we execute the all job. So the job tracker schedules jobs that have been submitted by the uh, clients, and it will assign job to the task tracker, and each task tracker consists of the map task and reduce task. And in this way the job tracker and the task tracker work. And let's see the phases of MapReduce. Basically, the MapReduce program is executed in three main phases. One is the mapping, another is shuffling, and the reducing. These are, beside there is also another optional phase which is known as the combiner phase, but we'll be discussing only about these three uh, phases. And um, the mapping phase, this is the first phase of the program, and there are two phases or two steps in this phase. One is splitting and another one is the mapping, and the data set is split into equal units called the chunks, or the in this splitting step. And there is in Hadoop, it consists of a record reader, and that uses the text input format to transform the uh, input, which splits into the key and value pairs. Basically, when the data is splitted, like when it consists of the data set is splitted into the key and value pair, and this record reader performs this splitting operation, and the key value pairs are then used as input to the mapping step. After splitting the data set, we get the key value pair, and this key is nothing but the reference to that value or to that data, and the key value pairs are then used as input to the mapping step, and this is only the data format that a mapper can read and or understand. So it must be splitted into key and key value format, and the mapping step contains coding logic that is applied to these data blocks. And in this step, the mapper processes the key value pairs and it produces the output that is same form, like the output of the mapper also is in the form of key value pair. And next is the shuffling phase. It also consists of two steps, sorting and merging, and this is the second phase that takes place after the completion of the mapping phase. It also consists of two main steps, sorting and the merging. In the sorting step, the key value pairs are sorted using the keys based on the key value, like the key based on the key, the values are sorted, and the merging ensures that the key value pairs are combined, and the shuffling phase facilitates the removal of the duplicate values and grouping of the values, and the different values with the similar keys are grouped, and the output of this phase will be keys and values, just like the mapping phase, like it also gives the output in the form of keys and values. And the final phase is the reducer phase, and in the reducer phase the output of the shuffling phase is used as the input, and the reducer processes this input further to reduce the intermediate value into the smaller value, and it provides the summary of the entire data set, and the output from this phase is stored in the Hdfs. And we can see here an example where the word count example of the MapReduce, and it this example shows the how three phases, the splitting, how these phases, how these are done in the MapReduce, like this mapping and shuffling and reducing. And here is the example of word count, and what we have to do is we have to perform the word count on the sample.txt using the MapReduce, and we will be finding the unique words and the number of the occurrences of those unique words in this file, which is input dot which is sample.txt. And first what we do is we divide the input into three splits we can see here uh, in the figure. Like the input consists of deer, beer, river, deer, car, beer, and it splits this input into three splits, and it's containing three words. Like the first split consists of the deer, um, deer, beer, river, and so on, and second car, and river, and so on. So this will distribute the work among the three map nodes. We can see here three maps, and then we tokenize the words in each of the mappers and give the hard-coded value 1 to each of the token or the words. And the reason behind giving the hard-coded value 1 is that, like, this one is that every word in itself will occur only once. Like this one means this is the number of words that is occurring in itself. And now the list of the key value pair will be created, where the key is nothing but the individual word, and the value is 1. We can see here the key and value. And for the first line, like for the deer, beer, and river, we have three key value pairs: deer 1, beer 1, and river 1. And the mapping process remains the same on all the nodes. We can see here the mapping, once the key value pair is obtained, then the mapping is same for all nodes. And next, in the shuffling, after the mapper phase, the a partition process takes place, where sorting and shuffling happens, so that all the tuples with the same key are sent to the corresponding reducer. uh, and in the reducer, so after the sorting, where we perform the sorting, and after the sorting, what is done here is like, the after the sorting and shuffling, each reducer will have the unique key and the list of the value corresponding to that key. For example, like the beer, 1, and a car will have 111, beer will have 11, and so on. And after the shuffling, each reducer counts the values which are present in that list values. Like we can see here, the reducer gets the list of values which is 1 for the beer, and it will be 2. Then it counts the number of ones in the very list and gives the final output, which is beer 2. Like in reducing, it will count the value for that key. And here, like, the beer will be counted as 2, and cow will be counted as 3, and deer will be counted as the 2. And finally, the output key value pairs are then collected and returned to the output file. Here, where we can see here in the output, it also gets the list with the key value format. Here the beer will be 2, car will be 3, and deer will be 2, and river will be 2. Actually, it's just a very basic example, but we can even use this MapReduce for like for parallel processing of some kind of very time consuming algorithms, like in training in machine learning algorithms, and other algorithms. But here it's just for understanding, it is the MapReduce is used here for simple word counting example. And let's see some advantages or benefits. There are two benefits of MapReduce. One is the parallel processing, and the MapReduce, as we are dividing the job among the multiple nodes, and each node works with the part of job simultaneously. So the MapReduce is based on divide and conquer paradigm, so which help us to process the data using the different machines, as the data is processed by the multiple machines instead of the single machine in parallel. The time to take the process, the time taken to process the data gets reduced by the tremendous amounts, as we can see here, like as we can see here, the as like the with the help of parallel processing, like we can see that the work can be done very fast. And another one is the locality, like the instead of moving data to the processing unit, we are moving processing unit to the data in the MapReduce framework. And like in traditional system, we used to bring the data to the processing unit and process it. But as the data grew up and became very huge, the bringing this huge amount of data to the processing unit posed to the following issues, like moving the huge data to processing costly. The moving the huge data to the processing unit processing is costly, and it deteriorates the network performance. And the processing takes time, as the data is processed by the single unit, which becomes the bottleneck, as we discussed in our previous class. So the if the master node can get overburdened and it may fail. So if we use the MapReduce, it allows us to overcome these issues by bringing the processing unit to the data. And so we can see in the above, like the MapReduce, it is data is distributed, and it's the data is distributed among the multiple nodes, and where each node process the data as a part of residing on it. And this allows us to have very this allows us to have the main advantage of having the reduction in cost, and the products and the product processing time is also reduced. And another, there are some other benefits, like cost effective. Hadoop has a scale out process feature that enables users to process or store data in cost effective manner, and it is scalable. It provides high scalable framework, and the MapReduce allows users to run applications from the many nodes. And data availability, like because of the replicas of the data which are sent to the various nodes within the network, which ensures the copies of the data that are available in the event of failure. So in this way, we get the benefits from the MapReduce. And it was all about the Hdfs and MapReduce. And in our next class, we will be discussing about the different big data analytics algorithms, and if possible, we will see some remaining like the some we'll discuss briefly about the Hadoop ecosystem components. But from next class, we'll be more we'll be discussing more about the different algorithms of the big data analytics.